Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. As you can see, I'm in home isolation at the moment, so the format's going to be a little bit different. So today I want to start a new playlist, and this playlist talks about some very interesting interactions between two rather different branches of mathematics. Firstly, number theory, and secondly, non-commutative algebra. And in this video today, what I want to do is I want to talk about a very classical problem in number theory. Okay, and that involves sums of two squares. And in so doing, I want to introduce a very, very important tool in number theory called the norm. Okay, so let's start by looking at what the problem involves. And what we'll do is we'll start by fixing some integer n, and that will be some positive integer. And the question here is simple enough. We're going to look at the following equation: x squared plus y squared equals n. Okay, so hence sums of two squares. The squares are x squared and y squared. Now you can look at this equation from different points of view. And if you're looking at it from the point of view of algebraic geometry, then what you want to do is you want to solve this for the variables x and y to be complex numbers, or sometimes just the reals. Okay, so of course, if you look at this over the reals, that's the one that most people are familiar with. X squared plus y squared equals n. You just get a circle. So it's a very geometric sort of thing here. In algebraic geometry, more often you want to solve these sorts of equations over algebraically closed fields like the complex numbers. However, what we want to do is we want to look at this in terms of number theory. So when you're looking in terms of number theory, what you want to do instead is you want to solve this over things which are very far from being an algebraically closed field. Okay, so for example, you want x and y to be inside the set of integers, or something like the rational numbers like that. And this problem is much harder than what you see over R. Okay, so that's a much more subtle sort of a problem and quite interesting from an arithmetic point of view. So since it's quite a difficult problem, we're going to make it a little bit simpler. What we're going to do is we're going to ask the following sub-question here. Okay, so what we're going to do now is we're going to vary this n. Okay, so we're going to ask for which integers n can you actually solve this equation here, this star here. That's what we want to do. And the answer is rather interesting. Okay, the answer involves the prime factorization of this n. So let's prime factorize this n. So n is equal to, say, p1 to the m1, p2 to the m2 times all the way down to pr to the mr. Okay, so this is solvable precisely when the following happens. Mi is even whenever pi is congruent to 3 modulo 4. Okay, so the answer as to which integers n can you write as the sum of two squares, so you can solve this equation here, x squared plus y squared equals n, just means that you can write this n as a sum of two squares. Interestingly, it depends on the prime factorization of n. And the answer is rather curious. It depends on the primes which occur, so the ones where pi is congruent to 3 modulo 4, the powers of those primes which can occur must be even. So you're probably thinking, well, this is rather curious. Why is it that factorization occurs in this? And the reason why that occurs is the following. Okay, so if you look at this equation here, star, what you can do is you can rewrite it. So that's n equals to, and I'm going to rewrite the x squared plus y squared as x plus iy times x minus iy. So in other words, you can factorize in the ring of Gaussian integers. Okay, so z adjoin I. So what's the ring of Gaussian integers here? Z adjoin I. What is that? Well, all that is just the set of complex numbers whose real and imaginary part are integers. Okay, so let's have a look at this problem further by introducing a rather important tool in number theory and in mathematics in general. And that's the norm. And we'll look at this in a very, very special case of a quadratic field extension. Okay, so let's see what we're looking at here. So we're going to start with some d, which is an integer, and it's going to be square free. So what do I mean by square free? So that just means that any divisor, there is no divisor which is a square. Okay, and so what we can do is we can adjoin the square root of d to q. So that's going to be now a quadratic extension of q, and it's a quadratic extension. So firstly, if d were a square and we adjoined it, then of course this square root of d would lie inside q, so you wouldn't get a non-trivial extension of q, but since it's square free, we get a quadratic extension of q. Okay, so what's important here is the notion of the Galois involution. And what that is it's going to be a map from q root d to q root d. I've called it sigma here. And it's defined easily enough as follows. Okay, so remember, firstly, this quadratic extension, what does it look like? So the elements inside here are just of the form a plus b root d. Okay, so here a and b are just rational numbers. And what we're going to do is we're just going to send a plus b root d to a minus b root d. Okay, so that's certainly a map from this q root d here to this q root d. So let's look at a very, very simple example of this. So that occurs when d is less than 0. So when d is less than 0, this b root d term here is purely imaginary. Okay, so basically you send the imaginary part of this a plus b root d to its negative. So all you're doing in this case when d is negative is sigma is just complex conjugation. So that's something that we're all very, very familiar with, complex conjugation. And there are lots of nice properties about complex conjugation. And just as there are lots of nice properties about complex conjugation, there are various nice properties about this Galois involution. Okay, so what's the first property? The first property here that I've listed is that sigma here is a ring isomorphism. Okay, so in other words, it preserves addition and also preserves multiplication. Okay, and that's something that you know for complex conjugation, and it's true even when d is positive. And now we come to the definition part of this proposition definition. Okay, and that's the norm of alpha of an element inside this q adjoin root d. And how is that defined? You can define it lots of different ways, but the way I'll define it is as follows. It's just alpha times sigma of alpha. Okay, so it's this product here. So it's alpha times sigma of alpha. And what can you say about this? Alpha times sigma of alpha. Well, you can write this out. So here's your alpha is a plus b root d, and you're going to multiply it by sigma of alpha, which is a minus b root d. So you get the difference of squares. So at the end of the day, you can write it out in terms of the a and b as a squared minus db squared. And if you notice something nice about this is that, well, a was a rational number, b was a rational number, and d was just an integer, so this is certainly a rational number. So you input here something in the quadratic extension, q root d, but this norm will send it to a rational number. And another important point here is the norm is multiplicative. Okay. So let's just go briefly and see why this is true. Okay, so maybe I'll give a slightly more sophisticated reasoning. Okay, I guess you can just check that sigma is a ring isomorphism by checking that it preserves addition and multiplication. But you may ask, well, where does this come from? Okay, where does this come from? Okay, so the way I'll do it is as follows. I'm going to construct various ring homomorphisms. So the first one I'll construct is from Q adjoin X, the polynomial ring with coefficients in Q. So just um, polynomials with rational coefficients. And I'm going to map this to Q root D. And the way I can do that is I can get a ring homomorphism. What does it do on Q? Well, it has to send all rational numbers, just two rational numbers. That's all it can do. But X, it can send to anything. Here, X, it can send to anything, any alpha. Okay, but we don't want a homomorphism from Qx to Q root D. We want something from Q root D to Q root D. And one way you can write Q root D is it's a quotient of Q adjoin X. Okay, so basically it's Q adjoin a square root of D. And one way to construct a square root of D is you adjoin X, but you make that X satisfy X squared equals D. Okay, so now by the universal property, how do you get a map from Q adjoint X, so this polynomial ring to Q root D, okay, if you want to do it to the quotient Qx over this X squared minus D, well, you have to send X to something which is satisfies X squared minus D equals 0. So alpha equals plus or minus root D. So if you send X to alpha equals root D, basically you get the identity. So over here, you'll get the identity on Q root D, but we choose the other one, and that sends root D to minus root D. So that's what you see with sigma here. That's the case where root D gets sent to minus root D. Okay, so that's a brief reason for why sigma is a ring isomorphism. And the next thing I want to say is why is it multiplicative? And that's quite easy to see. So you have norm of alpha beta. Well, that's firstly what you do is you multiply alpha beta times basically sigma of alpha beta. But remember, sigma is a ring isomorphism, so it preserves products. So this is alpha beta times sigma of alpha times sigma of beta. And since alpha times sigma of alpha is just, let me just go back down, it's just norm of alpha, and beta times sigma of beta is just norm of beta. So there you see the fact that n is multiplicative. Okay, so this norm turns out to be a very, very important tool in number theory. And just to sum up, one of the key features, firstly, in this case, we just look at the case of a norm from the quadratic extension Q root D to Q. Okay, so what it does is it sends alpha to this alpha times sigma of alpha, and this gives you a rational number, and this norm map is multiplicative. And they're things that are familiar for in the case where D is negative, okay, then what is this norm map here? Then since sigma is just conjugation, then alpha times sigma of alpha is alpha times alpha conjugate. So this is just the usual square of the modulus. Okay, so how is this relevant to our question of sums of squares? So we'll see that in this next slide. And more generally, what I want to do here is introduce the notion of norm equations. Okay, so we're going to have the same notation as before. We have a quadratic field extension, Q root D, as before. And now we're going to fix n, an integer. And a norm equation just means that you're going to solve norm of alpha is equal to n for alpha an element of, or let's just look at the integer version of what we want to do. Let's just look in the ring where you adjoin root D to Z. Okay, so this is the set of all a plus b root d, where a and b are just integers, like that. Okay, so how is it related to our original type of question, sums of squares? Well, we kind of saw that in the first slide, and the way we'll do that is we'll just write out what alpha is. Okay, so here alpha is equal to a plus b root d. A, b are integers. And then if you work out what is the norm of alpha, remember you multiply this alpha times sigma of alpha, and we saw this before, so it's a squared minus db squared is equal to n. Okay, so this is an equation. This double star, okay, this thing here is an equation where we're solving for integers a and b. And in the first equation, we're solving for alpha, okay? But alpha is inside this z root d instead, so not integers. They're elements of this ring here. And of course, the data that's required to write down such an element is 2 integers. Okay, so let's see how this relates to the original question. If d equals -1, what happens when you look at this double star? You get essentially what? This becomes double star is equivalent to just a squared plus b squared equals n. Okay, so you're just solving this equation a squared plus b squared equals n. So you're asking for how can you write this integer n as a sum of squares a squared and b squared. Okay, so the main point that I want to get across in this video here is that this equation here, star, is a much better equation to work with than the double star. Of course, they're equivalent, but for some reason, even if you're just interested in integers, z, it's good to look at extensions like this because this equation turns out to be much easier. And the reason why it's much easier to deal with is the following proposition. Okay, so let me show you how that works. Okay, so suppose you're asking the question, not so much how to solve this, but you're asking, well, when can you solve this equation? Okay, for which n? So the set n of integers for which this star is solvable, firstly is closed under multiplication. So that's something that you get. You can't say an equivalent sort of thing nicely if you work with this double star where you have a pair of integers. Okay, it doesn't really make sense for you to say, well, this pair of integers is closed under multiplication. That's not going to be something that works in this case. Okay, but inside here it does. Okay, so let's look at a specific equation. Let's suppose look at, or rather 2 equations here. We're going to look at norm of alpha is equal to 1 and -1. Okay, and let's put all the solutions of those 2 equations together. Then that turns out to be something rather interesting. Okay, and what is that? It's something, of course, that's a subset of z root d. And what subset is that? It's actually just a group of units. So hence the times up in the superscript here to denote the set of units inside that. And we know that that's a group, a multiplicative group. So that's rather nice that this set of solutions has some structure to it. It's a group. And once it's a group, it's a lot easier to describe what it is because, for example, if it happens to be an infinite cyclic group, to describe it, you just have to give a generator. And that's what happens in the case where D actually is positive here. It turns out to be an infinite cyclic group. And so you can just describe it by giving a generator. And that's an easy way to describe this infinite set of solutions by giving one solution which generates that group. Okay, so let's just see why this is true. Okay, so we'll look at part 1. And that's quite easy to see. Okay, so part 1. So suppose you have 2 integers which are norms. Okay, so for which you can solve this star here. So suppose n1 is such an integer, so you can solve it. So it equals norm of alpha 1, and n2 equals norm of alpha 2. Then n1, n2 is equal to norm of, remember, there's norm of alpha 1 times norm of alpha 2. But the point is that the norm is multiplicative, so this is just the norm of alpha 1 times alpha 2. So the product here is still just a norm. Okay, so it solves the equation. Okay, you can solve the equation here. For part 2, I won't do the whole proof, but maybe we'll just have a look a little bit as to why it's true. For example, so one way to say it is that, well, so what does it mean that the norm of alpha, remember this norm of alpha here, to be equal to plus or minus 1. What's special about plus and minus 1? They're the units inside Z. Okay, they're the units inside Z. And so you're saying the only elements of Z root D whose norms are units themselves. Okay, that's what's going on there. Okay, so let's just do one part of this. Okay, so suppose we want to say that the norm of alpha is indeed plus or minus 1. Okay, so suppose plus or minus 1 equals the norm of alpha. Then we have to show that this alpha is indeed a unit. Okay, so what can you say about this norm of alpha? Remember, this is the product of alpha and sigma of alpha. Okay, the product of alpha and sigma of alpha. And alpha, of course, was inside z root d. And remember, what did you do to get sigma of alpha? You just changed the plus b root d to a minus b root d. So this sigma of alpha is also in z root d. Now, what do we have to show? We have to show that alpha is invertible. And in fact, I'm going to produce an inverse for it. Alpha inverse is equal to what? Well, this since this alpha times sigma of alpha is plus or minus 1, that gives you the fact that alpha is invertible, and the inverse is in fact equal to plus or minus sigma of alpha. Okay, when you multiply this by plus or minus of sigma of alpha, okay, you'll get plus or minus of the norm, which will get you 1. Okay, so in this slide, we've looked at the notion of a norm equation. And these norm equations, the solutions are quite nice. Okay, so firstly, if you want to say when can you solve for this equation for which integers n, well, this set is closed under multiplication. And the other thing is that if you look at the very special case where the norm is equal to plus or minus 1, the set of solutions to both of these, then this is a group. Okay, so there's extra structure which will help you, for example, find more solutions, and also means that you can often use structure theory of abelian groups to describe the solution. Okay, so let's go back to our original interesting question, looking at sums of two squares. Which positive integers are sums of two squares? Okay, so in other words, so which positive integer n is the sum of two squares? And another way of writing it, our new way of expressing this uses the norm. So that is the norm of some Gaussian integer alpha in Z adjoin I. And just to remind you what the answer is, it depends on how you take this n and you prime factorize it. Okay, and you can't have any factorization, so it's not true for all integers n. Okay, so which integers n is it true? Well, it depends on this prime factorization, and the key thing is that well, the restriction is for some primes you can't have arbitrary exponent. So if mi happens to be odd, then you have to make sure that pi is not congruent to 3 modulo 4. Okay, and let me show you using this idea of norms why this is true. So unfortunately, I'll have to assume a little bit of number theory to give you the proof, but hopefully they're things that you've seen before. Okay, so what I'm going to do is I'm going to let S be the set of all of non-zero sums of two squares. Okay, non-zero sums of two squares. Okay, so the first thing that you need to realize is S is closed under multiplication. Okay, so to look at what is this S, so basically what you want to do is you're saying that this S, what you need to prove is that this S consists of all these integers which can have these sorts of prime factorizations. Okay, so the first thing to do is to say that well, you can get all these numbers and you can't get any others. Okay, that's basically what we want to say. We want to say that all these types of integers n, which have these prime factorizations, are in S, but you can't get any others. So let's see how that works. So firstly, we're not worried about even powers. Okay, so what I want to say is that if you have p as a prime, then p squared is inside S. Okay, well that's easy enough. So p squared equals p squared plus 0 squared. That's the sum of two squares. So of course that's inside S. Okay, so there's no problem there. So what other types of things that can you have? Well, if pi is not congruent to 3 modulo 4, then you can have any power of that prime. So for example, you can have any power of a prime p which is congruent to 2, of which there's only 1. So p equals 2. That's 1 squared plus 1 squared. So that's a sum of 2 squares, so that's inside S. So 2 is inside S, and so of course if you have any sum of 2 squares, you can multiply it by 2 or any power of 2, and that's still a sum of 2 squares, okay, since S is closed under multiplication. Okay, so what happens if P is congruent to 3 modulo 4? Well, if P is congruent to 3 modulo 4, then you can't have an odd power of P. So what we want to say here is that you can't have uh, P as a sum of 2 squares. So why is that true? So let's suppose you have a sum of 2 squares, a squared plus b squared. So one of the things that you should know is that if you have a square a, so you're either squaring a even number, which gives you something which is a multiple of 4, so that's congruent to 0 mod 4, or you're squaring an odd number, which is congruent to 1 mod 4. So when you look at a sum of 2 squares, that's going to be congruent to a sum of a 0, 1 with a 0, 1. So you can get 0 plus 0, 0 plus 1, which is 1, or 1 plus 1, which is 2, modulo 4. So what does that tell you? That tells you that if P is congruent to 3 mod 4, then for sure you can't write it as a sum of 2 squares, a squared plus b squared, like that. And that's where the restriction comes in. Okay. Of course, if you have an odd even power of P, it doesn't matter whether it's congruent to 3 or not, then that's okay. So we saw that even powers, since that's going to be a product of p squareds, and p squared is certainly a sum of squares, then you're okay. So the final thing that we have to do to make sure that we prove the rest of this theorem is to show that any prime p, which is congruent to 1 modulo 4, can be expressed as the sum of 2 squares. So this requires a little bit more knowledge, and hopefully you know some basic facts from number theory which allow you to prove it. Okay, so the first thing I want to do is I want to have a look at Z mod P. Okay, so this is the field, and if you look at the units inside that, the units inside this finite field turns out to be a cyclic group. So this equals, say it's generated by U, cyclic order P minus 1. So of course this multiplicative group here is just the non-zero elements, and since Z mod P has P elements, this multiplicative group has order P minus 1. So what does that tell you? Well, that tells you something about minus 1, so this is going to be important. Minus 1 equals what? So that's the square root of 1 inside here, and it's going to be unique. So what's 1? Well, 1 is, of course, since U has order P minus 1, you can write it as U to the P minus 1. And so if you do P minus 1, so here P is congruent to 1 modulo 4, it's odd, so it's U to the P minus 1 on 2. Okay. And then one way to write this is, remember, P is congruent to 1 modulo 4, so you can actually divide this by 4 and get an integer. So this is the square, this here minus 1 is the square of U to the P minus 1 on 4. So this is a square. So the main thing I want to say is in this Z mod P, minus 1 is a square. So that is minus 1 is a square in Z mod P. Okay, so why do we want to know about this? Well, let's look at this. So we're interested in the Gaussian integers and saying what are the norms of Gaussian integers? And we want to basically say that this P, which is congruent to 1 modulo 4, is a norm. So it is a sum of 2 squares. And the way we'll do that is we're going to look at the quotient of this Zi by the principal ideal generated by P. And one way to look at this, and this is why we looked at Z mod P, is rather than adding the I first and then quotienting out by P, we're going to quotient out by P first. And then to add the I, what we do is we rejoin x, so we need to adjoin a square root of -1 and factor out by x squared plus 1. And the key thing here is that, well, in Z mod P, right, we're going to adjoin a square root of -1 in this way, but -1 is a square. We said -1 is a square in Z mod P. So the conclusion is that this implies the fact that -1 is a square in Z mod P implies that this is not a field. So in this quotient ring here, okay, that's not a field. Now the other thing that you need to know is that Zi is a Euclidean domain, and in particular is a principal ideal domain. So this implies what? So if P, when you quotient out, is not a field, then P is not maximal, so P reducible. Say P equals P1 times P2, P1, P2. They're Gaussian integers, not units. Okay, you can have a proper factorization of P inside Zi. Okay, so now what we're going to do, so we're going to look at this equation here, and we're just going to apply the norm to it. Okay, so let's apply the norm to it. So you have the norm of P is equal to the norm of P1 times P2. So remember, norm is multiplicative. So what's the norm of P? So you've got to multiply P by its conjugate. So in this case, it's the complex conjugate, but P is real, so this is just P squared. And we said that P1 and P2 are not units, and by what we said before, that means that their norms are not units either. So this does not equal plus or minus 1, and this does not equal plus or minus 1. So that means that on the right-hand side here, we have a non-trivial factorization of this P squared. So remember, the norm of P1 and the norm of P2 are both integers. So that implies, so the norm of P1, so this product here, norm of P1 has to be P, and norm of P2 has to be P as well. So P equals norm of P1. And since this P is since this P is the norm of a Gaussian integer, P1, that means that it's a sum of two squares, so it's inside S. Okay, so since S is closed under multiplication, and we've checked that all the primes which are congruent to 1 or to 2 modulo 4 are sums of two squares, but no prime which is congruent to 3 modulo 4 is a sum of two squares. This completes the proof of that theorem. Okay, so this is a beautiful proof and I really like it, so that's why I wanted to share it with you. And let me just sum up by the moral to this story, and this is something that's very, very important in number theory, and that's the following. So this norm is a very important object. We've only looked at it in the very special case of a quadratic field extension of Q. But the key things that you're interested in is what things can be normed. So in other words, you're interested in what's the image of the norm map. Okay. And the other thing that we saw is that when the norm is plus or minus 1, okay, you get units inside rings of integers. And in particular, when you look at the norm equals 1, that's just the kernel of the norm map. Remember, the norm map is multiplicative, and if you look at the non-zero elements inside a field, then it's basically a group homomorphism on the multiplicative group of non-zero elements. And so here you're looking at the kernel. So the image and the kernel of the norm map are fundamental mathematical objects. So I hope you enjoyed this adventure in pure mathematics.